Hello students, welcome to this module, which is part 4 in our series of lectures on Introductory Nonlinear Dynamics, which is part of the course CHE 614 at IIT Kanpur. In the last module, we started understanding 2D systems. Specifically, we looked at linear 2D systems just to begin with. So in 2D systems, the dynamics of the phase trajectories are represented in a phase plane, because you just have two dependent variables. If you remember, you had two coupled equations, x dot and y dot. This is f1, this is f2 of xy, let's say. And we started with linear 2D systems. So these are linear functions of x and y. So you had the phase plane. Okay, and in the phase plane you have the two dependent variables x and y. Okay, suppose you had a stable fixed point. Okay, suppose you had a stable fixed point. Let's say the fixed point is at the origin, and if the fixed point is stable, then along all directions, okay, any initial condition will move towards the fixed point. Okay, so depending on the eigenvalues. So we remember we try to calculate the eigenvalues of the linear system. Depending on the eigenvalues, the approach to the fixed point, the shape of the approach to the fixed point will be different, but in general they will approach the fixed point in some fashion. Okay, all directions will lead to, this is called a stable node. So how do you understand whether this is a stable node or not? Of course, you have to look at the eigenvalues of this linear system, which we wrote in general as x dot is equal to ax. And if since we are considering a 2D system, there are two eigenvalues. Okay, there are two eigenvalues to this matrix. And if both lambda 1, lambda 2, if the real parts of lambda 1 and lambda 2 are less than 0, and I'm first assuming them to be real. Okay, so we'll come to complex eigenvalues in a bit. So then all the trajectories will flow towards the fixed point. And similarly, if you have an unstable fixed point, let's say the origin is an unstable fixed point, okay, then all trajectories will flow away in some fashion. Okay, now this is when lambda 1 both, if lambda 1, lambda 2 are real, okay, then lambda 1 is greater than 0, lambda 2 is greater than 0, then this is an unstable fixed point or an unstable node in the language of nonlinear dynamics. Of course, you may have a case when let's say lambda 1 is greater than 0 but lambda 2 is less than 0, and this is called a saddle point. And suppose you have the point at the origin, and in the last class we discussed an example wherein you had let me draw this, you had an eigen you have a stable eigenvalue and an unstable eigenvalue, and let's plot the unstable direction in red color. Okay, so this is the eigen direction or eigen vector corresponding to lambda 2. Okay, so let's call this eigenvector v2. This is the eigenvector corresponding to lambda 1. This is the eigenvector v1. Okay, so along this direction, if you start along this direction, obviously you will move towards this fixed point, whereas if you start precisely along this direction, you will move away from the fixed point. Then you can draw trajectories when you are not precisely on these two eigen directions. Okay, it will look like this. Okay, Okay, this is called a saddle point because there are two directions, one stable direction and one unstable direction. So far we have discussed only real eigenvalues. So now let's look at what if the eigenvalues are complex valued, okay, complex eigenvalues. Okay, that's also certainly a possibility. Now in this case there are two options, right? If lambda 1 and lambda 2 are purely imaginary, then what you will get are either they are closed orbits. Okay, what you will get are closed orbits, like the simple harmonic oscillator that we saw. So note that this is x and this is y, and you will get closed orbits in the phase plane. Okay, when lambda 1 and lambda 2 are such that lambda 1, and if they come, see the eigenvalue is governed by a quadratic equation. So the eigenvalues, if they are complex, will occur in complex conjugate pairs. That is, lambda 1 will be a plus ib, and lambda 2 will be a minus ib. If depending on the real part of lambda, which is a, you can figure out whether if you have a fixed point, whether that is stable or unstable spiral, in the sense that suppose you have a fixed point here. Okay, if both lambda 1 lambda 2 are if both real part of lambda 1 lambda 2 are positive, then things are going to spiral out. Okay, any point that you start out is going to spiral out, whereas if you have let me just see, if you have negative, this is again x y, if you have a negative real part, so this is a greater than 0. Okay, now this is a less than 0. Now this is a stable spiral, so things are going to come towards a spiral. Okay, this is an unstable spiral, whereas this is a stable spiral. Okay, now this point is called a center. The origin here is called the center. Now the direction of motion will be determined by the ordinary differential equation and their initial conditions. So we should not worry about it right now, the details of the direction, whether it is clockwise or anti-clockwise. Okay, all right. So in general, the two eigenvalues, remember in the last let me just recap the general quadratic that we wrote in the last lecture. We wrote that the characteristic equation is lambda squared minus tau lambda plus delta is 0, where tau is nothing but the trace of the matrix A and lambda is the determinant of the matrix A. Right, this is what we wrote in the last lecture for the eigenvalue. Right, now the two eigenvalues lambda 1 2 are therefore from the quadratic formula, right, half tau plus or minus square root of tau squared minus 4 delta. So, and you also know that delta is also given by lambda 1 lambda 2 and tau is given by lambda 1 plus lambda 2, because this is the trace of a matrix is also the sum of the eigenvalues. Okay, so when delta is less than 0, eigenvalues have real and opposite signs. Okay, and then you will have a saddle point. When delta is greater than 0, the eigenvalues are real with same sign, that is stable or unstable node, or they must be complex conjugate, in which case they must be stable or unstable spirals. Okay, so these are so when delta is greater than 0, if tau squared minus 4 delta is greater than 0, then you have nodes. This is, if this is greater than 0, then you have real eigenvalues. If this is less than 0, you have complex eigenvalues, right? So that's what I'm trying to say here. If tau squared minus 4 delta is less than 0, you have spirals, because the moment you have imaginary part, you will have spirals. Okay, suppose you have a 2D nonlinear system. So far we have been discussing 2D linear system. Suppose you have a 2D nonlinear system. Okay, x dot is f of x y, y dot is g of x y. Okay, now you have to find the fixed points by setting x dot is 0 and y dot is 0. So you'll have to solve these two equations simultaneously, nonlinear equations simultaneously, and that will give rise to the fixed points. Okay, now once you have found the fixed points, we can do a stability linear stability analysis of the fixed points. How do? You find that you say that I'm going to look at small deviations u and v about the fixed points. Then we know the two governing equations here. You substitute u and v out here, and then what you will get is u dot is f of x star plus u, y star plus v. This is nothing but I'm going to do a Taylor expansion in two variables, f of x star y star plus u partial f partial x plus at star plus v partial f partial y at star plus higher order terms which are neglected in a linear analysis. Okay, now by definition this is 0, because that's how you find the steady states or the fixed points, and therefore u dot is given by u partial f partial x at the fixed point plus v partial f partial y at the fixed point. Similarly, we have v dot is u partial g partial x at the fixed point plus v partial g partial y evaluated at the fixed point. Okay, now you can write this as in matrix form, which is nothing but partial f partial x partial f partial y partial g partial x partial g partial y times uv. Okay, now this is of the form u dot is equal to some a u, which is a linear system in 2D, which is what we discussed in the beginning of this module as well as earlier module. So this is the general linear 2D format, and this matrix is called the Jacobian matrix. This is the matrix of partial derivatives. It's called the Jacobian matrix. Okay, now in 2D nonlinear systems, right, and we know how to calculate the fixed points and understand the stability, what is the meaning of the eigenvalues, if the eigenvalues are real, if they are complex, all that we know from the discussions based on the previous module and the beginning of this module. Now there is one thing that I would like to discuss, that is the notion of a limit cycle. Okay, a limit cycle is an isolated closed trajectory. Okay, what do you mean by isolated? Of course, so in the xy plane, let's say if x and y are the two variables, okay, a limit cycle may look like this. Okay, this is an isolated trajectory because the neighboring trajectories are not closed. So the neighboring trajectories can be just if they come, they'll come close to this and then they'll join the limit cycle. Okay, and if you come from inside also, you will spiral out and then you will join the limit cycle. This is called a stable limit cycle, as opposed to an unstable limit cycle, wherein if you have an unstable limit cycle, again you'll have a closed trajectory, but things are going to move away as you start from when you start a little bit away, things are going to move away, and similarly when you start, things are going to move away from the limit cycle and go somewhere else, presumably to a stable node or something like that. So limit cycles are not like periodic orbits and simple closed orbits in simple harmonic motion, because there in simple harmonic motion you may have many orbits depending on the initial conditions, right? You may have many closed orbits, but in limit cycles there is only one orbit, and the oscillations are not the solution is not determined by initial conditions, unlike in the linear two-dimensional case. These are inherently nonlinear solutions. Okay, and this is a very special feature in two-dimensional systems. Okay, we'll come to limit cycles in a little bit when we discuss bifurcations. So now let's go to the topic of bifurcations in two dimensions. In 1D, we know that there is a saddle node, transcritical, and pitchfork. There are two types, supercritical and subcritical pitchfork bifurcations, right? These are the things that we learnt in 1D. What is bifurcation, by the way? A bifurcation is a qualitative change in the nature of the solution. A fixed point that was stable can become unstable upon changing of a parameter, the nature of solutions as a parameter is changed. Now all these bifurcations are also valid or possible in 2D. Okay. For example, let's take the case of saddle node. Okay, so I'm going to give a two-dimensional example of a saddle node bifurcation. X dot is mu minus x squared, okay, and y dot is minus y. Here mu is the parameter. Okay, so if I draw the phase plane for this particular this is x, this is y. Okay, now there are two solutions. So if you look at if you set the fixed points, rather, what are the fixed points? You have to simply set x dot and y dot to 0. Then x will be plus mu and x will be minus root mu, and y will be 0. Okay, so these are two solutions, and then there is of course the third solution. Okay, these are the only two solutions, I'm sorry. So we can draw the trajectories in the phase plane. Now this is a stable fixed point, this is an unstable fixed point, and we also know from previous experience with 1D bifurcations, that this one is an unstable fixed point. This is unstable, and this is a stable fixed point, right? So the trajectories are going to look like this. So you are going to come in the y direction. There is only just a exponential decay. So any initial condition will bring you close to this stable fixed point, bring you close to the x-axis, and then if you start on the x-axis itself, and similarly this is an unstable fixed point. Okay, so if you just start right here, you will flow close to this. Okay, but anywhere else you're going to go close to that fixed point. Okay, so this is a very, very trivial example. Okay, but because I've deliberately chosen this to be uncoupled, okay, they are not coupled equations. Now even if you were to have coupled two-dimensional equations, nonlinear equations, it turns out that if you find two fixed points, okay, now along a particular direction, it's not, in the previous case the fixed points lied on the x-axis, but there will be a particular direction, okay, along which the dynamics will be essentially 1D. Okay, now so this is how it's going to look. So this is a saddle point. Just exactly on this line it's going to flow here, but everywhere else things are going to go like this, whereas here everywhere else things are going to flow towards the fixed point. So essentially along this direction the dynamics is like a 1D event. Okay, so even in higher dimensions the essential things that we learnt about bifurcations in 1D systems are still valid. Okay, so all the three bifurcations will have their analogs in 2 dimensions also. Okay, but there is one important bifurcation that happens in 2 dimensions, 2 and higher dimensions, which is not possible in 1 dimension. That is called the Hopf bifurcation. Okay, now let's say that a 2D system has a stable fixed point. Now we can ask the question, in what ways will the stable fixed point become unstable? How will it lose its stability? Okay, how will it become unstable as a parameter is varied? That's what bifurcation is all about. Okay, now of course in order to understand stability we have to look at the eigenvalues of the Jacobian. So there are 2 cases. Okay, if both the eigenvalues are real, lambda 1, lambda 2 are both real, then and negative. So I'm plotting the so this is the eigenvalue plane, this is real of lambda, this is imaginary part of lambda, the eigenvalue. Okay, so now if both the eigenvalues are real and negative, so they are real, there are 2 eigenvalues, so one of them will slowly cross 0 as you change parameter. Okay, so this is the usual bifurcation that we have understood already in the context of 1D systems. But there is also another possibility. This is again the real imaginary axis. There is also another possibility. You have 2 eigenvalues that are complex conjugates of each other. So they have the same real part. Okay, so that's why the x-axis is the same, but y-axis they are symmetrically placed about the x-axis. So as you change a parameter, these two eigenvalues will simultaneously cross the real axis, the imaginary axis, and become unstable. Okay, so there are two complex conjugate eigenvalues simultaneously, two complex conjugate eigenvalues simultaneously crossing the imaginary axis. Okay, so the nature of the eigenvalues will look like this: lambda is equal to mu plus or minus I omega. So mu less than 0 is stable and mu greater than 0 is unstable. Okay, when mu is less than 0, then if you plot, let's say, x of t versus t, then you will have decaying oscillations. Okay, so it will look like this. If mu is greater than 0, this is mu less than 0. If mu is greater than 0, then you will have growing oscillations, but it's possible that this oscillation saturate to give rise to a new state, which is a limit cycle. This is a nonlinear phenomenon. So it is possible that these oscillations grow and get saturated. Okay, if that happens, this is called a supercritical Hopf bifurcation. Okay, now if you look at the Hopf bifurcation, you have initially you have a stable fixed point. Okay, and when before the bifurcation has happened, you have a stable fixed point. So it's like a stable spiral. Okay, it's going to appear like this. Now this is before the bifurcation. Now after the bifurcation, you have a limit cycle. Okay, so what this means is that this point has become unstable. So this is going to spiral out, and then eventually it goes to this limit cycle, but trajectories outside will converge to this limit cycle. Okay, this point has now become unstable, so the new state is a limit cycle. It's a closed path, but it's an isolated periodic path. It's not there are no neighboring periodic paths, so all initial conditions will flow to this if it is a supercritical Hopf bifurcation. But you can also have subcritical Hopf bifurcation, wherein for mu greater than 0 this is unstable, but for mu less than 0 also, okay, this is stable. The point is stable only if you are below this, within this closed path. Above this closed path, you're going to fly away. Okay, this is similar to the usual supercritical and subcritical bifurcations, pitchfork bifurcations in 1D systems. But the only added thing is that here the resulting state is a periodic state or a limit cycle. Okay, so now one last comment that I would like to make is that the bifurcations that we studied so far, there may be other possibilities also, but these are some of the most commonly seen bifurcations, namely saddle node, transcritical, pitchfork, there are supercritical and subcritical, and then Hopf, again supercritical and subcritical, These are some of the commonly seen bifurcations. These are observable for any n greater than or equal to 1, whereas Hopf is observable only for n greater than or equal to 2. That is, all these bifurcations are also possible in higher dimensions. Okay. So if you think of fluid mechanical system, right, like Rayleigh-Bénard convection, you have two surfaces and there is a temperature difference T1 greater than T2, gravity acting like this, right? And here also people have observed convection rolls, and this is an example of a state that is initially stable has become unstable, and it has given rise to a Hopf kind of bifurcation where you have oscillations in addition to a saturation. Okay, so this is a fluid mechanical system. A fluid mechanical system is governed by Navier-Stokes equations. Navier-Stokes equations are partial differential equations, right? Yet some of the simplest bifurcations that we understood in the context of 1D systems or 2D systems, okay, are observed even in PDEs. Partial differential equations can be imagined to be ODEs with variables of infinite dimensions, right? That is, if you imagine discretizing each of the velocities in the Navier-Stokes equation in a domain, and then if you continue to refine your discretization, then you will have an infinite dimensional vector, and therefore Navier-Stokes equations are infinite dimensional ODEs in some sense, right? But yet some of these bifurcations that we understood from the context of simple 1D or 2D models are observed experimentally even in Navier-Stokes equations or fluid mechanical systems. The reason is that even though fluid dynamical systems are infinite dimensional, all the interesting behavior happens along a special direction, and along that direction the dynamics is essentially 1D, and therefore all these bifurcations that we studied remain useful to describe even more apparently more complex fluid mechanical systems. Okay, so with this I come to an end to my set of lectures on introductory nonlinear dynamics. Through this I hope to have conveyed you a little bit of sense of how even in simple ODEs you can have unstable fixed points, and how a solution which is stable becomes unstable as you change a parameter, and you may go to another new state which is not the original state but a slightly different state, and so on, as in the case of supercritical bifurcations. So these are very, very useful ideas to have, and these will hopefully convince you that if simple ODEs can exhibit this behavior, more complex partial differential equations such as the Navier-Stokes equations used to describe fluid motion can also exhibit similar behavior. Okay, so what I'll do from the next class onwards is to give you some introductory lectures on function spaces and Fourier transforms before we plunge into the heart of hydrodynamic stability. So I'll stop here, and we'll continue in the next module. Thank you.